The real power of the chain rule comes from, well, two things. One is it allows us to just do lots of different derivatives because of so many functions are compositions of one or another. But probably more so is this notion of implicit differentiation that we'll talk about here today. And it's what it takes the chain rule to make this happen. Okay. So what we've looked at so far are functions like, y equals sine x, or y equals 3x to the 7 minus 2x cubed plus 4x plus 5 or something like that. I mean, you got functions like this. These are explicitly defined functions. You tell me what x is, I can calculate what y is. And you just plug it in, you figure out what y is. Okay. However, there are other curves that are described by reasonable equations, but they're not explicitly y is this function of x. It's more of an implicit situation. You got things like, one that I think most calculus students are familiar with is something that looks like this. X squared plus y squared, let's say, equals 25. Okay. This is an equation. There's a set of points in the plane that satisfies this equation. That is, their coordinates satisfy this equation. That's what we call the graph of the equation, is all the points that satisfy that equation. In this case, the graph looks like a circle of radius 5. I don't know how well I did there, but now, if I told you value of x and said what's y, well, you'd have to do some work. You plug it in, you got to move that over to the other side. It's not, y is not explicitly stated. Y is sine x, or y is this. Y is just part of the equation. But if I gave you a value of x, you could find y. Well, if I gave you a value of x, for each value of x, there's like 2 values of y that might be involved. But if I knew which one, let's say I knew I wanted to be on the top half, then at least locally to that point, there is something that looks like a function there, right? Down here, there's also something that looks like a function, so I'd have to know which one I'm at. But still, if I knew which one, then I've got essentially a function implicitly defined here. It's not explicit, it's implicit. But I notice as well that at that point, there's a unique tangent line. There's one point, there's one line that just comes in and just grazes that circle, hits at that point, and goes on. That would be the tangent line to the function. Tangent line to the circle. The slope of that tangent line would be the derivative at that point, right? Derivatives tell you slopes of tangent lines. So this is not an explicitly defined function, it's an implicitly defined function. And if we find the derivative of an implicitly defined function, then we are doing implicit differentiation, right? And here's the way we do this. Right? What we do is we essentially say, well, if y is a function of x, at least locally here, y is a function of x, we say this is, y is a function of x. Function of x. Y squared is also a function of x. X is a function of x. X squared is a function of x. So the whole thing becomes a big old function of x. And that's equal to this function of x over on this side. Now granted that this side in this example is a simple function of x. It's just a constant. But still, what I'm thinking of this as is I've got 2 functions of x equal to each other. The thing that I don't know is actually what function y is. I mean, it is a function of x, and I could, in this example, I could solve for this. I could subtract the x squared, take the square root, and say, oh yeah, y is the square root of 25 minus x squared. That's the function. But I don't want to do that. I want to do this without explicitly solving for y. But if you gave me an x, I could find y, so y is a function of x. So here we go. What I'm going to do is I'm going to say, take the derivative, why am I in green? Take the derivative of the left-hand side, a little bit of noise out in the hallway, I don't know if you can hear it, and that should equal the derivative of the right-hand side. if these two functions are equal to each other, and I'm saying they are, if I stay on this curve, then x squared plus y squared is always equal to 25. Well, then the derivative of the left-hand side should equal the derivative of the right-hand side. Well, the derivative of the right-hand side is easy. The derivative of a constant with respect to x is just 0. Derivative of the right-hand side, well, this is a sum. So I want the derivative of x squared, and then add to that the derivative of y squared. And in both cases, I'm taking the derivative with respect to x. Okay, so here we go. The derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x. Now remember, y squared is, y is some function. I don't know what it is, but it's a bunch of stuff, and all of that stuff is squared. So to take the derivative of something like this, how do you take the derivative of something squared? Well, you always work from the outside in, that this is a something squared. This is a power rule. The derivative should be 2 times that something. Well, that something is just, it should be 2. I can write it 2. 2 times that something to the first power, but then times the derivative of what's inside, right? Well, all I know about what's inside is I'm calling it y. So I got 2 times y to the first power times the derivative of y. I had to change the way I wrote that because it almost looks like a y prime there, but that's 2 to the first power. So what I have here is 2x plus 2y times dy dx equals 0, and I can solve for dy dx. So dy dx equals, well, 2y dy dx equals minus 2x. So subtract that over and then divide by the 2y here. And I've got dy dx equals minus 2x over 2y, and the 2's cancel out, so it's minus x over y. That's what I was looking for. I was looking for the derivative. I was looking for dy dx, and that's what I have now. Notice that because this was an implicit situation, my derivative isn't explicitly a function of x. It's got both x and y in it. But then I think, well, actually that makes some sense. I'm going to redraw my triangle. No, my triangle. What the heck is this shape? Circle. There we go. I'm going to redraw that circle and see that the derivative doesn't depend just on x. Because if you give me an x value, there's actually 2 y values that are associated with that x value here. And the slopes of the tangent lines at this point, this tangent line has a different slope than that tangent line. So the slope should depend on more than just x. It depends on y as well. For instance, in this case, notice that the point 3, 4 is on the circle. X squared plus y squared equals 25. Because if I take 3 and square it, that's 9. If I take 4 and square it, that's 16. And I add them up, you get 25. So the point 3, 4 is on that. So if this was 3, 4, right, then the slope, dy dx at 3, 4 equals, well, what am I saying it is? Negative x over y, so negative 3 over 4. So the slope would be negative 3/4 right here. If I look at this point down here, at 3 comma negative 4, dy dx equals negative x over y, but y is 4. Negative x over y. Y is negative 4. Let me just do this. Let me think again. I got the slope is negative x over y. My x is 3. My y is negative 4 with a minus sign out front. And so there we go. This is 3/4. And sure enough, that is a positive slope right down there, where it was a negative slope up here. Okay. It takes more than just the x-coordinate to figure out what the slope is, because it may depend both on x and on y, but that's all right. The formula that we got for calculating the slope did depend both on x and y. Actually, I want to just look at this particular example one more time, just because of the geometry of what's going on here. This was x squared plus y squared equals 25. We found that dy dx was equal to negative x over y. And in fact, I want to take a look at that from geometry point of view. That is, if this is the point xy, so this is the x coordinate, that's the y coordinate, then the slope of this radius is y divided by x. And one of the things about circles is that a radius is always perpendicular to a tangent line. So if these two lines are perpendicular to each other, then the slopes of perpendicular lines are negative reciprocals. And so the slope of this thing should equal the negative reciprocal of that. And sure enough, that's what it is. It's negative x over y. And that's what we calculated. I'm not always going to have this geometric interpretation, but it works nice here. In the next video, I'll do some more examples that are a little more complicated than this. But the idea is you have an equation that's relating x and y. You're thinking of y as a function of x. You just don't know what function it is. So you've got a big function of x on the left equals a big function of x on the right. Those two functions should have the same derivative. If the functions are equal, then the derivatives are equal. And so you take the derivative of both sides, remembering that when you take the derivative of something with a y in it, you're going to get a dy dx that pops out because you're doing the chain rule. You're saying this is something in parentheses, and so the derivative, take the derivative of the outside, but then remember to multiply by the derivative of the inside, and what's on the inside is y. And then you solve for dy dx and get whatever you get. Okay, we'll do a bunch more examples.